In this video, we're going to talk about the tangents of a circle. Now, to start things off, what exactly is a tangent line? Why don't we set the stage for tangent lines by talking about three types of lines in a similar context: external lines, tangent lines, and secant lines. So first of all, an external line to a circle is a straight line that does not intersect the circle. Why don't we go ahead and draw an external line to this circle here? So I want to draw a line that does not intersect the circle. So why don't we make it just go above the circle, say, and it'll look like this. There we go. So now I've got a straight line and it doesn't intersect the circle, so it's an external line. Okay, next up, a tangent line to a circle is a straight line that intersects the circle at exactly one point. So why don't we go ahead and draw a tangent line to this circle? It intersects the circle at exactly one point, so why don't we make it run through, say, this point right here. So we'll have our tangent line running through that point, and it'll look something like this. Now, one cool thing about tangent lines is that a tangent line is perpendicular to the radius which intersects the same point on the circle. So why don't we go ahead and draw a radius on the circle which intersects the same point. So this will be our radius, and that has to be perpendicular to the tangent line. So that's a right angle. All right, and then lastly, a secant line to a circle is a straight line that intersects the circle at 2 points. So why don't we go ahead and draw the secant line that goes through 2 points on the circle, say this point and this point. So we'll just go ahead and draw that line through those 2 points. Here it is. And there we go. There is an example of a secant line. Alright, so let's go ahead and work a problem. We want to solve for x and y in the diagram below. X is an angle adjacent to this 55-degree angle, and y is the side length of this base of the triangle. Also notice that the triangle's other two legs consist of a radius of the circle here and a tangent line to the circle. And hey, what do we know about the radius and a tangent line to a circle? Well, their intersection point makes a perpendicular angle. So this angle right here has to be perpendicular. It's a right angle, it's 90 degrees. So 55 degrees and x degrees together make 90 degrees. That means x equals 90 minus 55, which is 35. Okay, so there's x, and now it just remains to solve for y. And hey, since this is a right triangle, we can use the Pythagorean theorem. So let's go ahead and do that. So hypotenuse squared, y squared, is equal to side squared, so 2 squared, plus side squared, so plus 5 squared. We'll go ahead and simplify this, so y squared is equal to 4 plus 25, or y squared is equal to 29. So we go ahead and take the square root of both sides to get rid of that squared, and we just have y equals square root of 29. So there we go. There is y. And there we go. We've got x and y. We're done. Alright, so we've used the fact that the tangent line to a circle at a point is perpendicular to the radius of the circle which intersects that same point. But why is that even true in the first place? Well, in this problem, we're going to find out. In fact, we're going to prove it. Given a circle C with center O, we want to prove the following theorem. If line L intersects C at a single point P, then segment OP is perpendicular to L. So here we've got a diagram that sketches the setup. We've got the circle C with center O, and there's this line L which intersects C at a single point P. That means L is a tangent line because it only passes through that one point P on the circle. Now what we want to do is we want to prove that, given this setup, we must have that segment OP is perpendicular to line L. So we want to show that these two angles are right angles. But how do we do this? Well, the key to this problem is to use proof by contradiction. Proof by contradiction consists of three main steps. Step 1 is to assume that the theorem is false. So just to be very clear, this is the theorem that we're trying to prove is true, but the first step in proof by contradiction is to assume the opposite. We assume that it's not true. We assume that it's false. And the reason we do that is so that we can get to step 2. Step 2 is to find a contradiction that arises from the assumption that the theorem is false. A contradiction is just a statement that is absurd because we know it is false. So the idea is that if we assume the theorem is false, but that assumption leads to an absurd contradiction, then we know our assumption has to be wrong. And that would lead us to step 3. We conclude that the theorem is true. And that's just because it cannot be false. Otherwise, if the theorem were false, then it would lead to some absurd contradiction, as we discussed in steps 1 and 2. Alright, so given that setup, let's go ahead and jump into the proof. And let's organize ourselves with a divider here. Okay, so step 1, we assume that the theorem is false. So we assume that if line L intersects C at a single point P, then OP, the segment, is not perpendicular to line L. Our goal is to find a contradiction that results from this assumption. So basically we are assuming in our diagram here that these two angles are not right angles. And our goal is to find a contradiction that results from this assumption. In particular, the contradiction that we find is that the hypotenuse of a right triangle is shorter than a leg. And that's an absurd statement because the hypotenuse of a right triangle is always the longest side in the triangle. Alright, but that's jumping ahead. Where does this absurd triangle even come from in the diagram here? Well, what we do is we use O and P as vertices, and then we also make a third vertex at a point Q such that segment OQ is perpendicular to L. So basically we're saying that since we're assuming that OP is not actually perpendicular to L here, we just choose Q as the point where OQ is actually perpendicular to L. So why don't we say Q is over here? It really doesn't matter where we draw it on the line as long as it doesn't coincide with P because the argument will be the same. And we'll draw in that segment OQ. And Q is supposed to be the point such that OQ is perpendicular to L. So that would mean that OQ meets L at a right angle. I know in the drawing it doesn't look like it can possibly be a right angle because it looks like an acute angle. And that's really the whole point, because this will lead to a contradiction. But for right now, to be very clear, let's label this angle. This angle is supposedly a right angle, just so there's no confusion about this. Okay, so let's go ahead and write down this setup. So we'll just write down that we construct triangle OQP such that OQ is perpendicular to L. Now, if somebody were reading our proof at this point, they might complain and say, well, how do you even know that point Q exists in the first place? So we had better address that here. Now, the reason that we know Q exists is because given any point and any line, there is always a segment through the point which is perpendicular to the line. So let's go ahead and write that down. We know Q exists because given any point and any line, there is always a segment through the point that is perpendicular to the line. Okay, so that would defend against any complaint that Q doesn't exist. We are totally sure that Q exists. But there might be another complaint that arises. Maybe the person reading our proof would agree that, okay, Q exists, but why does it have to be different from the point P? What if Q is the same as point P? Then this triangle doesn't really exist because it's just a segment. So we should probably guard against that argument also. What we do is we say that, hey, we know that Q is separate from P because we said that segment OQ has to be perpendicular to L, whereas OP is not perpendicular to L. So let's go ahead and write that down. So we can say that, moreover, Q is separate from P because OQ is perpendicular to L, whereas OP is not perpendicular to L. Okay, great. So we've set up this triangle, and if anyone complains about it, we've got some bulletproof arguments that this triangle actually exists. Now let's talk about what makes this triangle absurd. We already talked about how this angle OPQ in the triangle has to be a right angle because we are supposing that OQ is perpendicular to L. So that means OQ and L intersect at a right angle. Now, if that's the case, then this is a right triangle with hypotenuse OP. And the hypotenuse is always the longest side in the right triangle. But really, that can't be right because no matter where we put the point Q, anywhere along the line L that's separate from the point P, the point Q is always outside of the circle. So that means the segment OQ is the radius of the circle and then a little bit more. So it's got to be bigger than OP, which is just a single radius of the circle. So that means OQ really needs to be the longest side of the triangle. And there's our contradiction. Okay, so let's go ahead and write all this down. First of all, we want to state that this is supposedly a right angle. So we're going to say that because segment OQ is perpendicular to L, that's just what we assumed when we constructed this triangle OQP. Because of that, we know that measure of angle OQP is equal to 90 degrees. And thus, triangle OQP is a right triangle with hypotenuse OP, because that's directly across from Q in the triangle. So that means then OP, the length of segment OP, has to be longer than the length of segment OQ. So OP is greater than OQ. And that's just because the hypotenuse of a right triangle is always the longest side. But now let's introduce the contradiction. The fact that OQ is actually the longest side because Q is outside of the circle, and therefore OQ is longer than a radius of the circle. So we can say that, but because Q lies outside of the circle, we must have that OQ is longer than a radius of the circle, such as OP. And there's our contradiction. We've shown that OP is greater than OQ here, and we've also shown that OQ is greater than OP. And that's just not possible. You can't have a number that is both greater than and less than another number. So we can just go ahead and say that this yields a contradiction. Okay, and now we are on to the last step. The last step is just to conclude that the theorem is actually true. So we can say that because of the contradiction, our assumption must be false. And the assumption here that we're referring to was the assumption that we made in step 1 here. The assumption that the theorem itself was false. So then, because our assumption is wrong, the theorem must be true. And that is, if line L intersects C at a single point P, then segment OP is perpendicular to line L. So there we go. Bulletproof argument that the tangent line is perpendicular to the radius. You can bet your life on it, it's true. Alright, great. So now we know a bit about the tangents of a circle, and in the future we'll continue to learn even more circle geometry.